Okay, in this class, we're going to cover blast design for masonry. My name is Sam Rubenzer. I'm the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in several Midwestern states. I have my engineering degree from the University of Minnesota and an MBA from Marquette University. We at Force, we're a team of engineers with a lot of different masonry design experience, and we've been consultants to the masonry industry since 2010.
I'm Ines Torre Bilal. I'm also a consulting engineer within Force. I am a licensed professional engineer in Illinois, and I hold a bachelor's, master's, and PhD degree in civil engineering with a focus in structural engineering from University of Illinois at Chicago. During my time with Force, I've had a lot of masonry design experience, and I'm also a consultant to the masonry industry.
Okay, that brings us to our learning objective for today. So what are some of the essential aspects of masonry wall design? So we cover a lot of different topics for masonry design, how to be more efficient with materials, how to be more effective with the way that we select to choose the different materials and how to build with masonry elements. And so certainly there's a lot of different things that are important for masonry wall design for a typical masonry wall. But certainly when we deal with extreme loading conditions like blast loading, certainly understanding what some of these aspects are, so maybe we can go even beyond then some of the basic steps that we can utilize to be more efficient with masonry design, but maybe now we actually take that and extrapolate it to even go beyond that to have more capacity when we need it. So what are some of the different material properties and code requirements to achieve a safe, efficient masonry design? So a lot of different things that we can choose from. How are some of the detailing choices? How do they affect the overall performance of masonry under the lateral or dynamic loads or blast loading conditions? And then how can conventional masonry be designed to be adapted for the extreme conditions such as blast or impact loads? So the first thing that we want to look at is we certainly have to look at the minimum design loads. ASCE 7 certainly going to give us guidance for how to do design for masonry for certainly gravity loads, and then lateral loads, wind seismic, tornado loads. TMS, the Masonry Society, is going to give us guidance for basis for the masonry design for flexural shear, bending, axial capacities. And then blast and impact design kind of extend these same principles to these short duration, high intensity pressure events. We're going to learn how to take and get loads from those analyses to be able to apply those to a common building or common masonry building. So we said before we're going to talk about some of the essentials for masonry design. What does that look like? Understanding properties for the block that we're going to use in masonry, the mortar that we're going to use in grout. What are some of the different assembly strengths that we should be using for typical masonry design? Is that going to be sufficient for an event like a blast loading? If you do have openings, what should be used for covering that opening? How should we be spanning above the opening? Using masonry lintels is going to be a very, very important part of efficient masonry design, but it's going to be, I think, some things that are maybe essential, for being able to handle high and significant load situations. So then, looking at the assembly and the masonry lintels, and then movement joints. Again, what do we want to do with the movement joints? Do we just want to put them away from the openings? Do we want to try to minimize or eliminate movement joints from the masonry elements to try to give a kind of a maximum wall size area that's able to, again, maybe dissipate some of the impact or high impact forces that you have with something like blast loads? So certainly for all designs in masonry, including blast loading, you certainly want to at least use the available strength for masonry, the available block strength. We know that we have a lot of different block material suppliers all across the country, and they have a variety of different ways that they make concrete masonry. So we definitely know that we have some variability for the different masonry materials, but we certainly want to be, especially when we're dealing with high load situations, we want to certainly available what's typically know or understand what's typically available for masonry design, but we also want to know where and how we can actually go beyond maybe some of those typical strengths. What are some of the different cost implications, if we're going beyond some of the typical strengths? So just a really quick chart to identify, some of the different material properties. So this is all based on table 2 within the TMS 602 code. We know that we have units in the far left column of a certain strength, and then we maybe utilize type S mortar. Now there's type M, type S, and type N. Type M or S are really going to give us the equivalent overall assembly strength, but S is going to be a lot easier for the masons to work with. So we typically stick with type S mortar for structural. Now certainly type N is also available. That's going to be something that would actually cause some reduction in overall capacity though. So again, we're dealing with blast loadings, heavy loadings. Maybe we want to stick with the type S mortar. So we have units of a certain strength. Again, in the left column, we know in the center column, we identify the mortar type, and then that gives us our overall assembly strength. So you can see if you had 2,000 PSI units, type S mortar, you'd have an overall assembly of 2,000. We know that if we have 3,250 PSI units and we use type S, we know that we would have 2,500 PSI for our overall assembly. We identify that as common when we do and have done research throughout the country for what units are typically available for masonry. We know that concrete masonry units are typically going to be 3,250 or higher. So we know that 2,500 is very common across the country. Now, there's certainly times where you have units that could be as strong as 4,500 PSI. Well, in that situation, we know that we can at least design to an F prime M of 3,000. Say we even need to go higher, we certainly can specify even higher strength concrete masonry units, use type S mortar, and then have the overall assembly tested in the prism test. So we know that we have other options for even getting higher strengths than what we see in this chart. And certainly you have another material in masonry. We have clay, structural clay units, not necessarily the emphasis of what we're talking about today, but we know that structural clay is even stronger than what we would have with concrete masonry, or as strong as some of the higher strength concrete that we can specify. But again, this is another option for seeing, if we need to go to a higher strength F prime M, we certainly have materials available either with high strength concrete or clay where we can approach a strength of masonry of 4,000 PSI. Now, certainly for looking at movement joints and the overall effects on the analysis for masonry, we know that we have a tech guide from Concrete Masonry and Hardscapes Association, CMHA, that has a tech guide 9-25 that gives us where the movement joints should go. So it's not per se in the code, but it's definitely going to be within this guide, this document that we utilize. It used to be called NCMA Tech 10-2D and a few other tech guides, but they cover where movement joints would go for reinforced walls. And we know that where movement joints go is going to be really, really important, for blast resistant walls, kind of minimizing some of these discontinuities, providing continuous horizontal reinforcement really allows us to improve the energy distribution and wall integrity, and maybe even disperse that energy and those forces through a larger area of walls. So we know that we can have reinforced walls. We know that we have control joints that are not needed at opening edges. That's going to be a really important aspect of it. Most openings, control joints could be as close as 2 feet. Unreinforced walls, again, not allowed for blast, but again, if we did have those, that's when we see those control joints at the edge of the opening. So we know that when we talk about movement joints, we still have a little bit of resistance with some designers, but certainly if you get into a wall that's going to be there for blast resistance, we know we can't have unreinforced walls, but and those would be the only walls that you'd ever put movement joints at edge of openings. And like I said, there's an option to forego movement joints, control joints, and provide additional horizontal reinforcement. And it's really going to be kind of useful for creating that larger continuous masonry element that would be more advantageous for blast load resistance. Goes without saying, when we talk about movement joints, and we've already talked about a few things that are pretty critical to the overall capacity of masonry based on movement joint locations, well, then don't you think it would be essential that we definitively define where those movement joints are located on plans, or definitively define where they are not to be located on plans? So it's going to be the responsibility of the designers to specifically locate them. We really don't want to have movement joints that are just kind of arbitrarily defined by a general note on the contract documents. We really want to be very specific where they need to be and where they cannot be in our designs. Again, just a quick visual. You can see some of the different guides, those different NCMA guides that were available, 1 through 4, but that's all kind of now included within the CMHA Tech Guide 9-25. Really, with those different guides, what we do have is we have these 3 different options for control joints and horizontal reinforcement. We have option 1, which is going to be some minimal reinforcement, and then some regularly spaced control joints. And that's going to be a pretty standard way to build with masonry throughout the country. We also have an option 2 that's identified in these guides, where you really minimize the number of control joints, or maybe eliminate them from a certain masonry wall definition, as long as you have a sufficient amount of horizontal reinforcement in your design. Option 3 would be kind of a combination of joint reinforcement and bond beams, and still having the liberty to maybe eliminate the control joints from a certain area of wall design. So again, option 1 is going to be there for controlling cracking. It's going to be a minimum amount of horizontal reinforcement and then some regularly spaced movement joints. Really, it's going to be control joints kind of based on that 25'4" or 1.5 times the wall height. It's kind of a pretty standard practice for design. But what we want to pivot to is looking at some of the different options that we have for masonry walls. We look at option 2 here, and you can see table 6 from the CMHA guide, where we look at the having enough horizontal reinforcement, a high enough level of horizontal reinforcement, 0.002 times the overall concrete masonry area, to provide at least that much horizontal steel reinforcement. So that it really enhances the ductility, allows for the wall to act as a single kind of diaphragm during a blast loading, really allows us to have a much better performance for an overall masonry wall. So again, we don't have to put in control joints, and we definitely don't have to put them into wall areas that are, at an increased risk for blast loading. Then option 3, we talked about option 1 with regular control joints and minimal amounts of horizontal reinforcement. Option 2 having bond beams and no control joints. And option 3 is kind of similar to 2, where we're really looking at having some bond beams and then also engaging horizontal joint reinforcement, and then still not having to put in control joints. So again, we see options 2 and 3 as some really good options for providing a much more resistant, resilient wall for something that would need to be blast resistant. So what does that look like? Again, option 1 is just going to be our kind of standard masonry wall, regular control joints, a minimal amount of horizontal reinforcement in our designs. So suitable for general design, provides some moderate continuity and energy distribution. I mean, it's certainly a very valid form of doing masonry wall design. But again, we see something like this, where we go to option 2, where we provide enough horizontal reinforcement to not need to put in control joints on a regular basis. Maybe we go several hundred feet, depending on the different situations. But you certainly have an improved wall from the overall energy distribution, and that continuous reinforcement, really horizontal reinforcement, improves the ductility, dissipates the load. Certainly can be a very high performing masonry wall within, and still, we talk about horizontal reinforcement, we know that we also have vertical reinforcement in this wall as well. So we're highlighting the horizontal, but really together with the vertical really does make a very robust design. And then option 3, again, if we have horizontal joint reinforcement that's in there, and then we maybe use a few less bond beams, could be a little bit easier to build, a little bit more efficient overall design, still has some of the same high performing capabilities that we had with the option 2 design. Now that we know we can also have openings, doors and windows are still can be in within blast resistant walls. Certainly those doors and windows are going to have to be design tested and detailed as blast resistant components. Certainly when we do that, we know that we have a little bit more vulnerable area. So making sure that those doors and openings um, you know, don't succumb to the pressures that you'd have with the blast loading. But say that we do, say that we have those elements. What do we want for the masonry wall around those openings? We certainly want to have a reinforced lintel that's able to pick up some of the loads, a little bit more heavily reinforced jam elements, but we really want that area around the openings to be extremely robust and able to handle the higher impact forces and stresses that you can have due to some of those openings that could be within that blast resistant wall. Now, certainly, again, you could do something like this. You could certainly have regular control joints and openings and some masonry lintels and some reinforcement that's going to be around all those openings. But again, it wouldn't really be suitable for a blast loading situation because there's so many discontinuities. There's so much here where you'd have some very high stress concentrations on minimal wall areas. So certainly pivoting to a design that looks like this, where we have certainly can have some openings, but we certainly have additional horizontal reinforcement in the lintels and then the horizontal joint reinforcement. We have enough of that horizontal reinforcement to really kind of push out those control joints to the edges of maybe this long wall panel. So it's going to be very suitable for high, wind load or tornado or storm shelter type situations, but it's also going to be very good for blast loading and kind of that high impact loadings that you'd have in that design. So just a little bit of a highlight about the lintels. Certainly the lintels in these elements are going to be very, very critical, making sure that we have masonry lintels where we have that horizontal reinforcement, that horizontal reinforcement that crosses with the vertical reinforcement. That two-way distribution of force is going to be really important and very critical to taking those loads. Again, if we do have those openings within the masonry walls within the blast area, certainly it's going to come with some higher stresses, higher forces. So we want to have some very good continuity and elements that you can have here with a masonry lintel. Certainly to be able to do this, we're certainly going to have a finite element analysis that's going to be really critical for not just looking at the lintel design, but looking at the overall elements of design. Really looking at a masonry lintel is going to be something that we certainly can do with the use of a finite element analysis. We can look and see how the lintel area, that lintel element, is able to distribute the forces to the wall panels on each side of the opening. So again, it's going to be really critical for the lintel design, but it's certainly the finite element analysis is going to be really important for the overall analysis that we're looking at. So looking at the entire building kind of in one model is going to be important for looking at the high impact loads or blast loads that you would have, understanding what those high force situations, how that force kind of carries through the rest of the building. So you can have a lot more accuracy when you use a finite element analysis versus kind of a crude single element type of analysis that you may be typically used to doing with masonry design. So we have a better understanding for continuity and complicated load pass, restraint effects. Maybe for this wall we want to consider fixed bases, fixed at the floor lines, the continuity that you would have if it's a multi-story type of design. So making sure that we understand all the different aspects of how that force is going to move through the building and going to be shared to the different masonry wall elements. And certainly we can take that wall and make it longer, like we talked about with minimal horizontal or minimal control joints and maybe a little bit more horizontal reinforcement. So using finite element analysis really does give us a lot of different abilities to look at masonry walls with a lot more complicated elements considered, which again make the wall much more resilient to some of those blast forces. So again, from structural detailing to blast design, really kind of looking at the masonry detailing, how it's going to affect the overall performance of the masonry wall and how that masonry wall is going to be able to then be well suited to be able to handle some of the different high demand loads that you would have from a blast event. Looking at reinforcement continuity, minimizing some of those joints to improve ductility, really looking at if we do have openings, how the different finite element analyses can be utilized to understand different stresses and forces as it kind of moves around some of those elements. And so what we're going to try to do is take some of these what I would call kind of high performing masonry walls, and then look at how that kind of can be incorporated into the blast analysis and blast design. So we're going to look at that next. So with that, I'll turn it over to Inez.
Thank you, Sam. So, as Sam mentioned, I'll be walking through how masonry structures really behave under blast loading. What kind of methodologies do we use for design, for checking, for detailing? And obviously, our focus today will be more practical. How do we go from code requirements to an actual blast-resistant masonry wall? So, I'll begin with some of the framework we're going to go over today. So what is aTFP or blast design? I'm going to get into that a little bit more in the next slide, but aTFP stands for Anti-Terrorism Force Protection Design, and the roadmap we're going to follow today starts with the fundamentals of blast loading, structural response, how masonry behaves under those loads. Then I'll go over design methodology, performance and detailing requirements, and finally a worked example to illustrate all the steps that we have been through. Now, looking at aTFP blast design, I mentioned it stands for Anti-Terrorism Force Protection. So it basically just sets the baseline threat for various explosive devices, and it really develops the performance goals we need for our buildings. So we're not really trying to eliminate all the damage. We're trying to first avoid collapse and protect life. But obviously, blast resistant design is focused on control damage of building envelope. The diagram on the right shows the pressure field around an explosion. So you could see the incident pressure, reflected pressure, and the standoff distance. The reflected zone here is really what drives that critical load on a masonry wall. Blast design requirements show up across multiple federal agencies. So we've got DoD facilities, VA facilities, federal facilities, etc. But each of these mandates different defined level of protection for the building envelope, including masonry walls. It's important to note that in practice, we mostly work under the first category, which is a DoD UFC framework, because the others are more specialized and kind of apply to narrower facility types. So the standards from the first group are the primary basis for most blast-resistant masonry design work. And so with that context here, let's talk a little bit more about the fundamentals of blast loads. They're very different from wind or seismic. They are short duration, really high intensity pulses. And to compare it to like a brief static load here, you can see in the graph the difference that static loads are constant while blast loads spike very sharply and then just kind of decay within milliseconds. So the duration is so short. Inertia really controls the structural response. So definitely not the same as a static type of load. So a blast is defined by the rapid release of energy, and we've got two main parameters here, which is the peak over pressure and the duration of the load. Reflection of this load is really critical because it can typically be 2 to 8 times the incident pressure, and that's really what drives the design. So this is why masonry walls facing the threat are usually the governing components in a masonry building. The blast wave itself is composed of two different parts. We've got the positive phase and the negative phase. The positive phase is a high intensity compressive pulse and typically can last from 5 to 30 milliseconds. And then comes the negative phase, which is the suction phase. It's shorter and then lower in magnitude, but almost never really controls the design for reinforced masonry walls. We still track it, but it doesn't really govern the design. We've got three main variables to consider when we look at blast loads, the explosive weight, the standoff distance, and the angle of incidence, which I kind of talked about earlier. So the pressure time histories are typically generated by the owner or the security authority. They use very specialized tools, which are can be one of the following, like ConWeb, SBEDS, or ATB Blast. So they use these to define the required input for the design. But the design engineer does not need to run the actual software or tool to define the load. So we usually use this input from the owner or the governing agency to continue further with the design for blast. So the applied pressure, PT in this case, becomes the forcing function. The equivalent mass is not the actual wall mass. It's an effective mass derived from mode shape participation. We apply the blast as a uniformly distributed load over the tributary width of the strip. This can usually be usually just 1 foot. Because really blast loads are assumed to act uniformly over rigid or semi-rigid wall panels. The model assumes rigid supports. This is a bit conservative, but the purpose of the SDOF analysis is to numerically solve for the maximum displacement, shown as X max here in the figure, which is the key output. So it's really a deformation-based analysis. And then from there, we compute ductility and support rotation for performance evaluation. The diagram here on the right shows that conversion. So we can see the wall's nonlinear resistance curve Rx, the effective mass that acts at the mid-height, and then we've got the blast pulse PT, which is applied as a forcing function to compute the dynamic response. This slide here shows how we simplify the pulse. The general PT curve is often idealized as a triangular pulse for design. So we still preserve that area because it really controls the structural response. But as I mentioned before, typically the negative phase, the suction phase, does not control the design. So we just simplify that pulse as a triangular load and calculate the area under the PT curve to obtain our impulse. We evaluate the wall's performance using three metrics I mentioned before: maximum displacement, ductility, and support rotation. Maximum displacement, X max, is really the backbone of the blast design. And then everything else is truly just derived from that original number. We've got the ductility ratio, which is the maximum displacement to that yield displacement, and we have the support rotation, is often the most direct indicator of the damage state. We also introduced DIF factors. Those are really important. The dynamic increase factors. We account for strain rate effects. And another very important factor here is the dynamic load factor, usually referred to as DLF, which is used when we idealize the blast pulse as a short duration triangular load. Because the actual blast really happens so fast, we need to account for significantly higher dynamic amplification. So DLF accounts for that higher amplification factor by converting the triangular pulse into an equivalent static load. So usually for short positive phase durations, the UFC guidance allows to use a factor of 2, and this is a conservative bound, of course, but we will see this in our next example. How do we incorporate our DLF or dynamic load factors into design? The concrete masonry has higher dynamic strength in both flexure and compression, so we apply DIF factors of 1.19 and 1.12 in compression, respectively. For shear, that factor is usually 1, and reinforcing steel gets a DIF factor of 1.17 for FY for yield strength. UFC does not really give a DIF factor for FU. And I think that's because we don't really rely on FU for blast, because ductility is just more important. But if you ever need to reference this factor, ASCE 59 allows for a factor of 1.05 to 1.15. This slide introduces the performance limits we use to evaluate whether a blast-loaded wall is acceptable or not. So these limits are deformation-based, not strength-based, and these are more general global limits. They're not material specific. They're just general performance objectives that are being set before we actually jump into looking whether we want to evaluate masonry, steel, or concrete, or any other type of material. So the three performance categories here are low damage, medium damage, and high damage. They come directly from UFC framework in ASCE 59, and they define the allowable ductility ratio and support rotation for the required level of protection. So it's important to note, like I mentioned, that these limits are very broad and they are the same framework used for steel, concrete, and masonry. And the criteria here, they're just um, general performance metrics, not unique to masonry for this slide. I'm going to get more specific with that later on. But here I want to note that low, medium, and high damage are deformation criteria, which typically mean that low damage is mostly elastic, medium, it includes some flexural yielding, but still controlled, and high damage, it's being near failure, but without collapse. Now, of course, for a unique or for an ideal design, low damage is the performance metrics that is preferred and typically used. The overall design philosophy is based on life safety first, control damage, but never a collapse. The most effective blast mitigation is increasing the standoff distance, and continuity and fixity matter more than absolute strength. Connections must really be robust because failure there negates basically all wall capacity, and low distribution in that case would really result in collapse. So let's look a little bit more on how masonry actually behaves under blast. Until now, we kind of covered more general principles on blast design and more understanding of this type of load. But now I would like to get a little bit more detailed on how this load is different for masonry, go over different concepts and governing standards for masonry. So I mentioned before that shear and anchorage failures are the more common failures here, and out of plane flexure is what really governs it because the blast just kind of pushes the wall inward if you visualize it. Mass really helps. Obviously, heavier walls absorb more impulse. Partial grouting is never acceptable. We design always fully grouted, continuously reinforced CMU, acting as a one-way vertical strip. And of course, for analysis purposes, CMU walls are assumed to act as a one-way vertical strip, unless you can really prove otherwise. This is a standard assumption here for UFC and ASCE guidelines because load redistribution is really limited. So the pulse is too short for membrane action to fully develop. So the panel behaves primarily in the direction of the shortest span. The primary documents that govern blast-resistant design for masonry, we've got UFC 3-340-02, which are the DoD engineering references for hardened structures and accidental explosions. And we've got the UFC 4-010-01. This one, it develops the minimum requirements and levels of protection and global performance requirements for DoD buildings. ASCE is really the civilian or civil engineering standard for blast protection. It provides performance criteria, acceptance limits, and additional detailing guidance. Also, of course, it's important to note that the practical approach for masonry includes obtaining loads and response criteria from UFC 3-340-02 and ASCE 59. But then anything that has to do with capacity and detailing goes back to TMS 402-602. And from the ones highlighted in red in this slide, these are the standards that typically are available for everyone to use, and the other two that have a different type of requirement are just for official use only. So we focus on the UFC frameworks and the ASCE 59 that are available to public, and engineering can use those. So DoD's minimum design criteria provides a baseline anti-terrorism requirement for all DoD buildings. So it defines minimum standoffs and different acceptable damages here. These requirements are based on a baseline external explosive threat, and they reference the UFC 3-340-02 for explicit blast design. So like I mentioned, this standard requires every new DoD building and of course any existing building undergoing any major repairs or renovation to be designed to resist a specified explosive threat. Only reinforced CMU meeting TMS 402-602 is acceptable for exterior walls, but I'll cover that in more detail. So, like I mentioned, let's look into the minimum requirements themselves. So, standard one focuses on standoff distances. So, it requires that a DoD building be located at least 50 feet inside that controlled installation parameter. This typically ensures that the baseline explosive threat cannot be placed directly against that facade without crossing a monitored boundary. So if a facility is closer than 50 feet to that installation parameter or it's outside it, the minimum aTFP criteria, they do not apply. So instead, that threat level must be reassessed and the building may require explicit blast design. Standard 2 requires 33 feet of unobstructed space around the building. The intent here is to prevent that area from making sure to avoid local pressures. And like, for example, if you have a 6-inch explosive placed behind equipment or trash containers, you would be avoiding that. So that's focused on standard 2. And of course, vehicles are allowed to park in the zone, but only if they meet the security restrictions and they do not violate the standoff conditions. Standard 9 focuses directly on exterior wall systems, and this is where the masonry specific requirements really become clear. So first, the building must still meet that 50 feet perimeter rule. This distance is considered sufficient and for typical code design exterior walls to provide acceptable protection. But because of this, if the wall meets standard building code loads, and the building sits at or beyond that standoff requirement, a full blast analysis is generally not required. So to summarize this, or to add more to this concept, unreinforced masonry is not permitted. For new construction, reinforced CMU designed per TMS 402-602 automatically satisfies the minimum blast requirement when standoff distance requirements are met. And then if the facility requires more than the baseline level of protection, let's say it's a critical facility, or it's a building with reduced standoff, then a full blast design per UFC and ASCE 59 is mandatory. So for most standard DoD buildings at proper standoff, reinforced CMU is compliant and no further analysis is required. For higher threat or reduced standoff projects, we must go beyond TMS and of course run explicit blast calculations as required by the owning facility or agency. Now, I'm going to go over some of the most recent research done in this field. This slide here shows results from the Air Force Research Laboratory phase. It's a full-scale blast loading. And of course, these tests are extremely valuable because they validate how reinforced CMU actually performs. The wall used here is 8-inch fully grouted CMU, number 5 vertical bars at 40 inches on center, and we've got joint reinforcement at 16 inches. Of course, fully grouted reinforced CMU demonstrated excellent ductility, as you can see from the figure to the right. The wall behaved in a controlled flexural manner, which is exactly what we want for a blast. A variable that was tested here was brick veneer, so it was tested both with and without insulation. The veneer contributed additional mass, which kind of improved that resistance, but did not really create composite action. So it simply increased the inertia, not really part of the structural resistance. However, it's important to note that the veneer did not show any negative structural effects or caused any instabilities. And another important outcome of the study is that the veneer ties performed well, so they transferred the load without overstressing the insulation layer. And just because that's usually, it's important to understand the standard tie configuration, whether it can withstand blast induced loads or not. Within the same study, phase 2 was performed to show the opposite, how partially grouted CMU behaves under identical blast conditions. So phase 2 tested the partially grouted CMU system These tests were really critical because many legacy buildings were constructed using partial grouting, especially if it was like an older school or an older commercial building. The partially grouted walls performed really poor under blast, as you can see on the right figure. Um, and the ungrouted cells uh, collapsed under this pressure pulse. You can see the webs being fractured and the wall just ejected debris in a way that resembles unreinforced masonry. So this is why modern blast design requires fully grouted cells and continuous reinforcement. Now let's kind of shift our focus from those test results to the formal response limits in ASCE 59. So previously I mentioned that we had some global limits, but now we're going to focus more on material specific limits that are really more reactive limits for masonry here. So the next few slides outline the deformation-based response limits taken from ASCE 59, and these are the limits that we use to classify the expected performance of the wall. So they're primarily intended for new masonry design under blast loads. And for reinforced CMU, we compare the SDOF calculated ductility and rotation to these boundaries to determine whether the wall falls into low, medium, or high damage categories. These two tables in the slide provide definitions on the acceptable level of damage and the structural member classification, followed by the next slide, which continues the description of the ASCE 59 performance curves. Here we can see the various definitions for component damages and classification of damage based on structural component type and level of protection that we covered in the previous slide. This is probably one of the more important slides here that really presents the deformation limits for masonry walls subjected to blast loading. It differentiates between reinforced masonry and between flexure and combined flexure plus compression behavior. The table is divided into 4 damage categories: superficial, moderate, heavy, and hazardous. Each category is defined by 2 parameters, which is the ductility ratio and the maximum support rotation, which we know are both very important parameters. The top half of the table is for unreinforced masonry, which behaves in a brittle manner and is prone to a lot of fragmentation under blast. You can actually notice here how unreinforced masonry has extremely limited allowable deformation, and support rotation limits are just very small. It's very important to note that we typically do not use those for design because unreinforced masonry is not permitted at all, but these are just values that were practically tested, and they're just reported for reference to actually show the behavior of unreinforced masonry. In reinforced flexural behavior, the allowable deformation increases significantly because steel reinforcement can carry the tension and provide that necessary ductility. For moderate damage, the rotation limit is around 2 degrees, meaning the wall can crack, heal, and deform in a controlled way without losing that structural integrity. For heavy damage, the rotation limit increases to 8 degrees. And for hazardous conditions, that goes all the way up to 15 degrees, which typically does not mean collapse. It just means that the wall remains standing, but it has just really large deformations, possibly creating unsafe conditions on the interior. The second row for reinforced masonry represents combined flexure with compression. And here, basically, that means that the wall can carry axial load. Under combined loading, the allowable deformation is reduced because the walls are not purely bending members in this case. For moderate and heavy damage, the rotation limit is 2. This reflects the fact that axial load stiffens the wall and reduces available deformation capacity. So if these calculated parameters fall within moderate or heavy bands, and that matches the project's level of protection requirement, the design is acceptable. If deformation exceeds the heavy or approaches hazardous limits, we conclude that the wall fails the performance requirements, even if that flexure strength passes. So the earlier slide I mentioned gives the global performance categories, whereas this slide here gives the precise numerical limits behind those categories. And these are typical limits for material specific for masonry. And we look at them as more reactive limits and how we can actually consider how much deformation is acceptable for reinforced masonry to achieve the required level of performance. So with that, let's go through a full blast wall design checklist. If we were to design a masonry wall for blast, what would be the typical steps to follow? Start by defining level of protection and acceptable damages as step one. We use the UFC frameworks to establish minimum standards and set response limits, including ASCE 59 standards. Next is load definition. Define the explosive weight, standoff, and environment, internal or external, depending on where that's located. Generate PT pressure time histories using ConWeb or SBEDS. As I mentioned before, these tools are really specialized, and this type of curves are usually provided by the owner. Then idealize the wall as a one-way strip. Determine effective mass, stiffness, and participation factor. Next, incorporate materials and dynamic effects, DIF, DLF, all the needed parameters to actually perform the analysis. Material properties come from ASTM standards and TMS 402-602 capacity equations. We build a resistance deflection curve, which is the main aim of this SDOF model. And after applying the dynamic increase factors, we run the SDOF time history to get displacement and rotation. So then we confirm that the wall stays within the required ductility and rotation limits. Finally, we check strength and detailing. We verify flexure, shear, anchorage, and splice requirements using TMS 402-602. As also Sam mentioned, detailing is critical for blast performance. Fully grouted cells, continuous reinforcement, vertical bars near control joints, reinforced lintels, bond beams, proper hook anchorages. These are all great practices for detailing for blast. And poor detailing undermines all analytical capacity. And with that in mind, let's walk through a full example here. This is a reinforced CMU wall under external blast. We're going to target a low damage condition level of protection with basically the ductility less than 4, support rotation less than 3. So this is just a stable ductile wall behavior without loss of integrity. The example focuses on a 12-foot tall, fully grouted 12-inch CMU wall with a 1-foot analytical strip. Reinforcement and material strength are provided here with F prime M being 2500, FY 60 KSI, and the appropriate applicable dynamic increase factors for masonry 1.19 and for steel yielding 1.17. And now we apply the blast load. So the peak reflected pressure here is considered as 12 psi with a duration of 12 milliseconds. This is converted to a line load of Q equal to 144 pound per inch, and a dynamic load factor of 2 is used for short triangular pulses, which I mentioned before that this is conservative, but just because blast is such a high intensity pressure, we account for a factor of 2, which is recommended by the UFC framework. The section here uses 2 number 7 vertical bars per face at 8-inch and 2 number 5 horizontal bars per face at 16-inch. Next, we calculate the flexural capacity. The compression block depth is calculated as 2.8, and then the nominal moment strength, MN, is calculated as almost 649 kip-inch per foot. Applying the reduction factor, the design strength is almost 589 kip-inch per foot. So the demand here, after applying the dynamic load factor of 2, it's 498 kip-inch per foot. So the flexure passes with a good margin, so that's okay for design. And next, we verify shear. Shear steel area is 0.62-inch square per foot strip. Both steel and masonry contribute to total shear capacity, and that's a calculated value of 39 kip per foot. Design shear itself is 29.25 kip per foot, and the demand VU is 20.8 kip per foot after calculating or after applying the dynamic load factor of 2. Shear also checks out. So I just want to add here that it's really important to note that using DLF of 2 is a conservative approximation, just because it's SDOF time history is the governing method that determines whether the wall truly meets the required level of protection or not. So DLF equal to 2 is kind of a design tool, but it does not substitute the full time history. And a full-time history verification shall be performed when doing these type of analysis. And with that, this concludes the overview of blast-resistant masonry design here, from load generation to SDOF modeling, from detailing to final capacity checks. And I'd be happy to answer any questions. Both Sam and I have provided our contact information here. So if there's any questions, please let us know. Thank you.
Thank you very much.